Hello and welcome. I am so glad you could join me. Today we're diving into a topic that is, and I mean this, absolutely essential for your success in WAEC, NECO and JAMB physics, the concept of field. Now, I know it can sound a bit abstract, right? But trust me, this is a very high scoring area, and by the end of this session, you're going to feel so much more confident. This is the foundation for gravity, electricity, magnetism, the whole shebang. So let's get ready to smash it. Okay, so let's jump right in with a simple question. Have you ever really stopped to think about it? Why does a ripe mango always fall straight down? Why not sideways? And how in the world can a magnet just pull a nail towards it without even touching it? It seems like magic, but it's not. It's physics. And these are perfect everyday examples of fields at work. These are forces that can act over a distance across what looks like empty space. And that's the mystery we're going to solve today. So, what's the official definition you need for your exams? Here it is. A field is just a region in space where an object, like one with mass or an electric charge, will feel a force without anything physically touching it. Think of it as an invisible area of influence. The Earth creates a gravitational field all around it, so any object with mass that enters this area, like our mango, is going to feel that pull. The key phrase here, and I want you to burn this into your brain, is non-contact force. Examiners absolutely love to test if you understand that concept. Right, here's our game plan for today. First, we're going to break down the gravitational field. Then we'll tackle electric and magnetic fields. After that, we get to the most important part. We're going to solve real past questions from your exams. And we'll finish up with a quick summary and some top-tier tips to help you grab every single mark available. Sound good? Let's get started. Okay, first up, the gravitational field. This is the one we're all most familiar with, simply because we live inside it every single day. It's the reason we're stuck to the ground and not floating away, and it's what keeps the moon circling the Earth. It really is all about the universal pull of mass. So, what causes a gravitational field? It's simple. Mass. Anything that has mass, you, me, this pen, the Earth, creates a gravitational field around it. And the whole thing is governed by Newton's law of universal gravitation. Now, this formula you see on the screen, you absolutely must know it by heart. The force F is equal to big G, that's the gravitational constant, times the two masses, m1 and m2, all divided by the square of the distance between their centers, r squared. And let me repeat that because it's a common mistake. R is the distance between their centers, not from their surfaces. So how do we actually measure the strength of this field? We use a value we call gravitational field intensity, which we represent with a small g. It's defined as the force experienced per unit of mass. So the formula is G equals F over m. Now watch this. This is pretty cool. If we substitute the big formula for F from the last slide into this one, you get G times big M times little m over r squared, all divided by little m. The little m at the top and bottom just cancels out. And what are we left with? Our second super useful formula, G equals Gm over r squared. Big M here is the mass creating the field, like the Earth. This G is also what we call acceleration due to gravity. You know, about 9.8 meters per second squared, right here on Earth's surface. Now, to help us picture these invisible fields, physicists use something called field lines. For your exams, especially for diagram questions, you have to know their properties. For gravity, it's pretty straightforward. Number one, gravity is always attractive. So the field lines always point inwards, right towards the center of the mass. Number two, the field technically goes on forever. It has an infinite range. It just gets weaker and weaker the farther you go. And number three, where the lines are bunched up or denser, the field is stronger. That's why G is strongest right at the surface of the Earth. Excellent! You are doing great. Let's move on to our next section, which deals on these exact same ideas. We are now going to look at electric and magnetic fields. These are all about the forces of charge, and they are responsible for, well, pretty much everything in our modern world, from lightning in the sky to the phone you might be watching this on. Okay, this comparison table makes the differences really clear. Let's look. An electric field that's caused by electric charges that are just sitting still, but we call them static charges. A magnetic field, on the other hand, is caused by moving charges, which is just another name for an electric current, or of course by magnets. Now here's the biggest difference from gravity. While gravity is only ever attractive, both electric and magnetic fields can be attractive and repulsive. You know the rules. For charges, opposites attract, likes repel. For magnets, north and south poles attract, but two north poles will repel. Now this is where you can save yourself a lot of memorization stress. Pay attention. The force in an electric field is described by Coulomb's law. Just take a close look at that formula. F equals K times Q1 times Q2 all over R squared. Does that look familiar? It should. It's got the exact same structure as Newton's law for gravity. Instead of masses, we have charges, Q. And instead of big G, we have Coulomb's constant, K. And guess what? The same pattern works for the field intensity, E. It's KQ over R squared. If you can see that pattern, it becomes so much easier to remember both sets of formulas for your exam. Okay, for magnetic fields, the formula is a bit different. The force on a charge Q that's moving with a velocity V inside a magnetic field of strength B is given by F equals QVB sine theta. Now the key thing here, and I can't stress this enough, is that the charge must be moving. If V is 0, the force is 0. Simple. And you have to pay very close attention to that sine theta at the end. Theta is the angle between the direction the charge is moving and the direction of the magnetic field lines. This is so critical. Why? Because the force is strongest when the charge cuts across the field at 90 degrees, since sine of 90 is 1. But, and listen up, because JAMB loves this, if the charge moves parallel to the field lines, the angle is 0, and the sine of 0 is 0, meaning there is no force at all. Let's quickly compare the rules for drawing field lines, because this is a favorite for WAEC diagram questions. For electric fields, the rule is simple. Field lines always start on a positive charge, and they end on a negative charge. They never ever cross. For magnetic fields, it's different. The lines always form closed loops. Outside of the magnet, they travel from the North Pole to the South Pole, but inside, they go from south back to north to complete that loop. Knowing this difference is key to getting those diagram marks. Alright, you have been brilliant so far. We've gone through the theory, and more importantly, we've tackled real exam questions. Now it's time for the most important part of our session, applying what we've learned to real past questions from WAEC, NECO, and JAMB. This is where we turn knowledge into marks and build that real exam confidence. Let's do this together. Okay, here's one from WAEC 2007. The question asks, which of the options does not represent the action of a field force? The options would be something like A, an apple falling, B, an iron pin being attracted by a magnet, C, two like charges repelling, and D, pushing a wheelbarrow. So let's think it through. The falling apple, that's gravity, a field force. The iron pin in the magnet, that's a magnetic field. The charges repelling, electric field. All of those are non-contact forces. But pushing a wheelbarrow, you have to physically touch it, right? It is a contact force. So the correct answer is D. You see, that's a direct test of the definition we learned at the very beginning. Now for a JAMB question from 2016. If the direction of motion of a charged particle is parallel to a magnetic field, the path of the charge will be A, a straight line, B, a circle, or C, a parabola. Now this goes straight back to what I was warning you about. The formula is F equals QVB sine theta. If the particle moves parallel to the field, what's the angle theta? It's 0 degrees. And what's the sine of 0? It's 0. So the whole force becomes 0. If there's no force acting on it to change its direction, what does it do? It just keeps going in a straight line. The answer is A. You see how they love to test that angle? Alright, Let's tackle a NECO calculation from 2009. The question says, the gravitational field intensity at a location x in space is 2/5 of its value on Earth's surface. If an object's weight at x is 4.80 newtons, what is its weight on Earth? Okay, don't panic. Let's break it down. We know that weight, W, is just mass times g. Since the object's mass doesn't change, its weight is directly proportional to g. This means we can set up a ratio. Weight on Earth over weight at x equals g on Earth over g at x. Now the question tells us that g at x is 2/5 of g on Earth. So our ratio, g Earth over gx, becomes g Earth over 2/5 g Earth. The g Earth on top and bottom cancel out, leaving us with 1 over 2/5. And when you divide by a fraction, you just flip it and multiply.
So that becomes 5 over 2. Now we just solve for the weight on Earth. It's going to be the weight at x, which is 4.80, times our ratio, 5 over 2. And that gives us a final answer of 12.00 newtons. It's all about setting up that ratio correctly. Fantastic work. We've gone through the theory, and more importantly, we've tackled real exam questions. Now, let's pull everything together into a powerful summary. I want you to think of this next part as your ultimate toolkit, your quick revision guide for the night before your exam. This table right here, this is the heart of the entire topic and has every single key formula you need for fields. Seriously, I want you to pause the video, take a screenshot of this or write it down in your notes and look again at that beautiful pattern between the gravitational and electric force laws. It's the same structure. One is about mass, the other is about charge. The magnetic force formula is the odd one out because it depends on velocity and that all-important angle. Knowing this table by heart, I promise you, is half the battle won. Now, let me give you some pro tips to help you avoid those common silly mistakes that cost students marks. First, if a question mentions field lines, always draw a quick, clear, and labeled diagram. Examiners actually reward that. Second, before you plug any numbers into a formula, check your units. Make sure everything is in standard SI units, that's meters, kilograms, and coulombs. And finally, remember that common trick. In the gravity and electric formulas, r is the distance from the center of the object, not from its surface. Don't let them catch you with that one. And I really want to leave you with this message. You sat here, you've listened, you've learned, you've even practiced with me today. You have absolutely everything it takes to understand this topic and to answer any question they throw at you. You can do this. The key now is just practice, practice, practice. The more past questions you solve, the faster and more confident you are going to feel when you walk into that exam hall. If you found this lesson helpful, please do me a huge favor. Like this video, share it with your classmates and friends who are also preparing for WAEC, NECO, and JAMB. And subscribe to our YouTube channel right now so you don't miss the next topic. Also, make sure you visit ExamKP.com for thousands of free practice questions and answers. Let's smash these exams together.